So the first question on the test was about finding the net force on a charge which was -3 microcoulomb, and there were two other charges. One of them was -1 microcoulomb over here at some point at a distance of 0.1 meter, and the other one was also 0.1 meter, and this charge Q2 was given to you to be +1 microcoulomb. You had to find the net force on this charge. You can, the first thing to do is what? Yeah, free body diagram. Everybody should be first drawing a free body diagram. There are two forces on this. One is due to this one, and you can see it's a repulsive force since both charges are negative. So the repulsive force on this is going to be this way. Let's give it a name, F1. There is a force on this due to this charge, and this is positive and this is negative, so this charge is attracted. And again, I'll only draw the free body diagram of this because I have to find the force on this. Okay, so this, there is an attraction here, so the force F2, let's give it a name, F2 is this way, and right? And so the thing is, these are the two forces. That's it. Is everybody comfortable with this? So what would be, Is everybody comfortable with this? And so the thing is, what would be the direction of the net force then? You can see if you have two forces, you know, one of them is like this, F1, the other one is F2, you can always move these arrows so long as you don't change the magnitude and direction. So this is your force F1 here, this is your force F2, you can see the resultant will be the vector that joins the tail of one to the head of the other one pointing like this, right? And in fact, is the magnitude of F1 and F2 the same? Yeah, the magnitude will be given by, remember from Coulomb's law, the magnitude of force between two charges is, you know, K, Q1 magnitude, Q2 magnitude divided by the distance between them square. So you can do that for this and this, you can do that for this and this, and you can find what F1 and F2 are, and you can see magnitude of F1 and F2 are the same because Q1 and Q2 have the same magnitude, right? So basically, you know, if these two have the same magnitude, you know that the angle theta, which will be what? Yeah, it will be 45 because it will be tangent inverse of what? F2 divided by F1, that will be tangent inverse of 1, which is 45 degrees. So the angle is 45 degrees south of, say for example, if you chose this to be positive x-axis, then it's south, it's basically below the positive x-axis, right? And I'll let you find the magnitude of the force, you know, F net magnitude will be square root of F1 square plus F2 square, which you can write as 2 times square root of 2 times F1 square, right, which will be square root 2 times F1 magnitude. Is that making sense, folks? Okay. The second question was asking you about this situation. Basically, you had a cube and there was a charge at the center of the cube, and you were asked, there was some charge Q which is positive at the center, and you were asked about the flux through one face. The thing is, we can use Gauss's law to say that the total flux through the whole cube is how much? Q enclosed over epsilon 0. So that will be Q enclosed is the total Q divided by epsilon 0. And since the charge is at the center, will the flux through each of these faces be the same? It will be. And so flux through one face should be just 1/6 of this, right? Okay, then the next question is saying locate the point or points at which the electric field due to the two charges is 0. So you were given a situation like this where you had a charge Q1 which is plus 4 coulomb, and you had another charge over here Q2 which is plus 2 coulomb, and you are asked for a point where the electric field is 0 between them. You are told that the distance between them is 3 meters. Will there be any point like that? Yeah, there will be, and in fact that point better be somewhere along the straight line joining the two charges, right? How do I know that? Because, and moreover, that point should be closer to the weaker charge. It should be closer to the weaker charge because I know that only then will the influence of this charge be cancelled by the influence of this charge. So let's say that the point is somewhere over there. You know, let's say that this is point P where we are saying that the electric field is 0, right? And let's say that this is at a distance x away from this. Then we know that the distance from this one is going to be 3 meters minus x meters, right? Okay, we also know that the electric field at this point due to this charge will be away from it. Let's say this is E2, and the electric field due to this charge at this point will be away from this because this is also positive, so that's E1. If I call this the positive x direction, you can see we have EP equal to 0 means E1 minus E2 equal to 0 because E2 is in the negative x direction. That means E1 must be equal in magnitude to E2, and you can see that E1 is what? K Q1 divided by what distance square? This distance, right, which is 3 minus x meter. So this is 3 minus x meter square, and that should be equal to this, which is K times Q2 divided by this distance is the distance of Q2 from this point. So that would be x square. K and K get cancelled. So basically you can now plug in the value of Q1 and Q2 and solve, right? Is that making sense? Okay. The third question was asking for the third question gave you this situation. You were told that you have very, very thin balloons which are insulating. So there is one balloon here, and this balloon has charge plus Q on it, uniformly distributed. Okay, and then there was another balloon here which was concentric with it, and that was also an insulator, and that had a charge minus 4Q. Folks, there shouldn't be any talking. This had charge minus 4Q uniformly distributed on it. And there were 3 parts to this question. You had to find the electric field at some distance r. By the way, the radius of this balloon was given to you to be A. The radius of this big balloon was given to you to be B. And you had to find the electric field somewhere over here at a distance r which is less than A, at somewhere over here at a distance r which is between A and B, and somewhere over here where the distance r is greater than B, right? Okay, so let's try one by one. So part 1 is r less than A. What would be the electric field? Let's say we were looking at some point here. What would be the electric field at this distance r? Yeah, because remember what we have been saying, these charges are uniformly distributed, right? I mean, if you're not sure about this, the easiest way to do this is to draw a Gaussian surface, right? Use Gauss's law, and what you will see is that in all of these cases you will find that the electric field turns out to be K Q enclosed over r square when the charges are uniformly distributed, right? When you use Gauss's law. So in this case, this is my Gaussian surface, there is no Q enclosed here. Q enclosed is 0 because this charge is outside and that charge is outside. So the electric field in this case is 0. Okay, what about case 2? Case 2 is the case where r is greater than A but it is smaller than B. So somewhere say between A and B, between these two balloons, right? So let's say over here. Now we have to find electric field at a distance r away, let's say over here, right? In that case, you know, again you can think about doing a Gaussian surface. This time if you do a Gaussian surface that passes through the point where you're trying to find the electric field, you can go through the same exact procedure and you will again find K is equal to K, sorry, electric field is magnitude is K, Q enclosed over r square, right? But what is Q enclosed in this case? It's just this Q. Do you see that this is not enclosed? So this minus 4Q is producing 0 electric field anywhere here. So the answer here will be the magnitude of electric field is just K, Q enclosed is Q divided by R square. And what about the direction of electric field? Yeah, remember this minus 4Q is producing no electric field. It's only electric field produced by this positive charge which is uniformly distributed here, and it will be radially outward at every point, right? From the symmetry of the situation, if you ask me what is the electric field here, it will be radially outward here. Is that making sense, folks? So it's radially outward, not inward, outward. Okay. Okay, what about case 3? Case 3 is the case where you have to find the electric field somewhere over here at a distance r away, where r is greater than b. In this case, again, could you use the same kind of reasoning? This time you should choose a Gaussian surface passing through this point, and you do the procedure and you again find that the electric field magnitude is K, Q enclosed over R square. This time for this case 3 where R is greater than B, what would be the Q enclosed? Is all the charge enclosed if you're trying to find the electric field at a distance R greater than B? Yeah, so it's minus 4Q plus Q, which is minus 3Q. And so the electric field magnitude in this case will be, well, if you're just finding the magnitude, you can just say it's K3Q over R square, but the direction is, yeah, is radially inward. Right, is that making sense that the direction is radially inward? Because there's minus 3Q and plus, minus 3Q charge, net charge that is producing the electric field. One way to think about it, this is almost like saying that you can think that that there is a point charge minus 3Q here, and this point charge is producing an electric field at some point R which is greater than B, right? Isn't it as though all this charge on the surface of these spheres was at the center of the sphere for a point which is outside the sphere, right? Okay, so that time it's radially inward. You know, if suppose this was not minus 4Q, if this was just minus Q, how would the answer change? Yeah, there won't be any electric field here outside, right? Do you see that? Okay, so if suppose this was plus Q and this was not minus 4Q but minus Q, the electric field outside everywhere will become 0, wouldn't it? If this was not this but just minus Q. All right, let's move on. We'll quickly go over the conceptual questions. So the one question was asking about something that we have done several times, which is you have some kind of a charge comb or something, you bring it close to, I think you even did an exploration problem like this. You know, you have a metal cylinder, you can even think of it as a ball if you like. What happens when you bring a metal ball? This is metal, whether it's a metal ball or tall metal cylinder, it's the same thing. You would induce minus charges on one surface and you would induce plus charges on the other surface. What is the electric field inside? It's 0. So if the electric field everywhere inside is 0, is there any force on anything inside? No. So no matter what you put here, there is no force. There is not going to be any force on any charges, free electrons, anything. So the only charge separation is here because the electric field everywhere here is 0. So the correct answer here was only charge separation at the two surfaces, and the electric field is 0 everywhere inside. So this is answer B. The choice that was correct was B. Okay, question 2. Question 2 was asking you about a case where you ground a conductor versus when you don't ground a conductor. What is the difference between the two cases? So you have some conductor like this. This is a conductor. Here also this was a conductor or metal, and you bring some charged thing here, right? What will you do here? You'll induce negatives here and positives here, exactly like this, right? Okay, now suppose I do another case where I actually ground it now. So you have this thing that you bring close to it. This is negative, this is positive. Now if you ground it, what do you think will happen? Do you see that these positive charges don't want to be close to these positives, right? So electrons will come from the ground, exactly, electrons come from the ground and they'll neutralize these things, these positive charges. So you don't have any net charge on this surface, right? Is the force between this metal ball and this thing more here than here? Yes, the attraction is greater here. So there's more force here than in this case, because here if you think about it, these charges are attracting this, but these charges are repelling it. So if you find the sum of them, there's less attraction between these. In this case there's only attraction. Does that make sense? Okay, so that was the case there. The third thing says you have a hollow sphere which is made of perfectly insulating material and it's electrically neutral, and now you put a small amount of negative charge at one place. What would happen to that charge after some time? What do you think will happen? So the question saying you have an insulating ball, this is an insulator, you put some charge over here, let's say this is plus Q or minus Q, whatever you want to call it. Do you think that charge will move around? If it's an insulator, no, it's not going to move, so it's just going to stay there because it's an insulator, right? Okay, the next question was asking you to find the direction of electric field. So it said that you had a situation like this. There are 3 points A, B and C. There was a charge which is -1 unit here, +1 unit here and +1 unit here, and you had to find the direction of net force on this charge. You can see that this charge will be attracted towards this, so there will be a force, let's call it F of A this way. This charge is repelled from this, so there will be a force F of C that way, and you can see that the resultant of these two will be pointing somewhere like this, right? And in fact if these two charges are exactly equidistant, which they are, the force will be at 45 degrees here. So none of the choices that you're given is correct. So the answer was none of the above. Okay, the next question was saying to you that you had two charges. One of them was -2 units, and the other charge at some location which we call point B is +1 unit, and the question asked you to show the direction of force on these charges, right, and also the magnitude with the arrows. So you can see these two charges have opposite sign. Will they attract? Yes, they will attract. Will they attract with the same exact force? Yes, from Newton's third law they'll attract with exactly the same force, so the length of these force vectors should be the same. Okay, the next question was asking you about a situation in which you are told that you were told that you have something like this where you have some charge plus Q2 here and you have another charge plus Q3 here, and there's a charge this is some charge Q1, and you are told that because of these two charges the electric field, the force on Q1 is pointing in the positive x direction. This is what you are given as the positive x direction. So if the force on Q1 due to these two charges is in the positive x direction, what should be the sign of Q1? Negative. It better be negative, because only then will it be attracted towards this charge, right, with some force, let's say F2, and it will be attracted towards this charge with, let's say, some force F3, right? Does that make sense? And then in fact in this case you are told that the net force is this way, so you know that if you find the component of F2 in this direction, you know, let's say F2x, and this direction, let's say F2y, and you find the component of F3 which is F3x and F3y, these two forces must cancel each other out, right? If the net force is given to you be along positive x direction. This is given. Now the question was asking you, what do you think will happen? What do you think will happen if we add an extra charge in addition to these things? So this is still the same, minus q1. If you add another charge which is positive somewhere over here, what will this charge do? It'll exert a force on this, right? Which way will this charge feel a force? Will it be attracted towards that? Yes. So this will be an additional force F's of q on this charge, and this is in addition to this thing, right? So in addition to the old force, this is F net old. So you can see that now the net force is more, but it points in the same direction. Is that making sense? So net force is more, but it points in the same direction. All right. The next question was saying you have a hollow metal sphere and you put a small amount of excess charge at some location. What happens to it after some time? What do you think will happen? Yeah, this time it is going to uniformly spread out on its outer surface because equilibrium will be established very soon, and we know that electric field inside the conductor should always be 0 in equilibrium, right? So in this case, even though you may have put the charge, you know, this is your metal ball, and you may have put some charge q here, you know, after some time it will not stay there, it will just kind of spread out uniformly on the outer surface. This will be the equilibrium situation, right? The charge has spread out. Is this making sense? So that the electric field everywhere inside stays 0. All right, the last question was asking, choose all of the following physical quantities that are vectors. Is electric field a vector? Yes. You definitely talk about electric field having an angle 30 degrees south of west or north of east or with positive x-axis. It is a vector quantity. In fact, we know F is equal to QE. So the direction of force on some charge at some point will be parallel to the direction of electric field. What about electric flux? No, electric flux is a scalar quantity. In fact, you can see flux is Q divided by epsilon 0, right? Or another way to write this is integral of E dot dA. Do you see that it's a scalar product? Is everybody seeing that it's a scalar product? Scalar product means that it doesn't have a direction. Remember, flux can still be positive or negative, just like temperature can still be positive or negative, or work done can still be positive or negative, but work done is not a vector quantity. Flux is not a vector quantity. Does that make sense? So these things are scalar quantities. You don't say these things are pointing 30 degrees south of west or something. That wouldn't make sense. Scalar can still be positive or negative. That's okay. What about electric charge? That's a scalar again. Again, charge can be positive or negative. That's okay. But the thing is, charge does not have a direction. You don't say the charge is pointing 30 degrees south of west. That wouldn't make sense. So the only thing out of these that was a vector was electric field. Charge is a scalar quantity. Any questions, folks? Please.
On the first conceptual one that's in the left board, on the right side of it, yeah. For the electric field, like within the conducting cylinder to be 0, like within the small thing itself, doesn't there have to be a positive charge on the inner surface of the left side? Because
you mean, suppose if there is an inner, you are saying that there has to be plus here?
for the electric field inside that to be 0, otherwise it would all be to the left.
No, actually, see that's what I was, and that's what I was trying to tell you, for a long time, that the inner surface will never have any charge on a conductor unless you have some charge in the cavity itself. Otherwise there will not be. So what I'm trying to say is that suppose you're thinking about the electric field here, let's say, if you find the electric field due to these charges, these charges will produce their electric fields like this, let's say. These negative charges will have their electric field, let's say, towards them, and these positive charges will have their electric field, away from them like this. If you add up all these, the contribution of all of these charges, it will add up to 0 there. But not just there, everywhere inside this conductor the electric field, adds up to 0. I mean, that's the way charges will distribute themselves. So in these surfaces, how charges will distribute themselves, it will depend upon, you know, exactly how much charge there is, how close it is, etc., how it's distributed, right? This charge that you bring close. But the point is that never will charges go to inner surface of a conductor, never, unless you have some charges inside. Does that make sense? So all the charges are always on the outer surface of the conductor unless there is charge inside itself. Only the charges inside do anything to the inner surface. One thing I wanted to say is that I gave you a question about electric field and I told you, tell me how to find the electric field in this situation. Suppose if this question was not about electric field but it was about electric potential, because right now we are discussing electric potential, and so if this question was about electric potential and suppose I said to you this, suppose I said to you, okay, there is a charge plus q here and there's a charge which is 4 times stronger plus 4q here, is the electric potential 0 anywhere? Can you talk to a person next to you about this question? So everybody should take 1 minute to discuss this with each other. So suppose in the next exam I give you a question which doesn't say find a point between these two charges, both of which are positive, somewhere where the electric field is 0. Suppose instead of that the question was asking find a point somewhere where the electric potential due to both these charges is 0, and if there isn't any such point, why isn't there such a point? Explain. What would you say? Talk to a person next to you.
Did you have to add that? Kate called me last night. I'm a recitation at 8. So I got up at I was up at like 2:30 and I kind of keep going. She never answered.
All right, anybody from the last row? Any thoughts, folks? Anybody has any thoughts? Is the potential 0 anywhere here? What about in this situation? Is the potential, electrical potential 0 anywhere due to these two charges? No, the answer is no. So the answer here is no. It is not 0 anywhere. You know, the answer to this question is V equal to 0 anywhere? The answer is no. Why is it no? Anybody wants to explain? Why is the answer no to the electrical potential due to two positive charges not being 0 anywhere? Please. Well, it is a scalar, that's true, and because of that, if you think about it, if both charges are positive, what potential are they going to produce? If you remember, potential due to a point charge is K Q over R. This is the potential produced by a point charge due to a point charge q at a distance r away from the charge, right? So do you see that if I think about some point, let's say over here at a distance x away from this, and say at a distance, you know, let's call it x1 and at a distance x2 here, do you see that the potential at that point V will be equal to V1 plus V2? Let's say that this is charge q1 and this is charge q2, and is everybody seeing that the net potential at this point will just be K Q over x2 plus K times 4Q over x1. Do you see that this is positive? This cannot be 0. When can the potential be 0 though? Can anybody think of situations where potential will become 0 due to 2 charge, please?
When the radius is so far that it's a high thing, so it automatically makes it approach 0, the fraction.
Okay, so one case that maybe you can think of is potential infinitely far away from these charges, but I'm saying suppose you were not thinking about infinitely far away, but you have 2 point charges. Can you think of a case when the potential is 0? Yeah, for example, you know, if I told you that this is not a positive charge, this is say a negative charge right now, is it possible to make the potential 0 at some point? Yeah, this time it is possible because you know if it's a negative charge, remember the potential due to a negative charge will be K and then whatever is the negative value there, right? So minus 4Q in this case divided by R. So in this case, if I say V is equal to V1 plus V2, I can find a point. Let's say that the whole distance here was 1 meter. If this whole distance is 1 meter, then one thing I know is that x2 can be written as 1 meter minus x1, right? So if I'm trying to find a point, first of all, will this point be closer to minus 4q? No, it better be closer to this thing, right? So in some sense, I should be thinking of this point, maybe the way I have drawn it, it's not the best way to draw it. So this is my x1, and this is the point where V is equal to 0, and that means V1 plus V2 is equal to 0, and let's say this distance is 1 minus x1 meter. And so what do we have? We have K Q over 1 minus x1 equal to plus V2, which is K times minus 4Q divided by x1 should be equal to 0. Is everybody seeing that since potential is a scalar quantity, we don't draw any arrows or anything. We just simply write down whether it's a positive potential or a negative potential. Do you see that? And so here, if you see, we get K Q over 1 minus x is equal to K 4Q divided by x1. All I'm doing is I'm taking this to the other side and negative becomes positive, right? Let's divide throughout by K. If I divide both sides by K and Q, I get this, and basically what I get there is that, notice if I cross multiply, I get x1, or we can even call it x, we don't have to call it x1, is 1 minus x1. So that means x1 is equal to 4 minus 4x1. Let's take all the x1s to one side. So this is 4, that means 5x1 is equal to 4, and that means x1 is equal to 4 over 5 meters. So that means the place where the potential is 0 is at a distance of 4/5 meter from the stronger charge. So it's 1/5 meter from here. Is this making sense? Can you think of other points here where the potential could be 0? Because I claim actually there are lots of points where the potential is actually 0. Can you think of why? Because you know, if the potential is a scalar quantity, do you think that this thing could happen at other places, not necessarily on the straight line joining the two charges? Go ahead.
If there's like a straight line.
Yeah, it may not be perpendicular bisector, but the thing is, if I think of some other point, right? Let's say that you know there is a point, some point over here, where this distance, right, and this distance are such that you know KQ over R1 turns out to be exactly equal to K times 4Q divided by R2, then the potential will become 0 there. Do you see? Because we are not talking about vectors, we are not saying directions cancelling out. That would never have happened for electric field. Do you see what I'm saying? You cannot cancel the electric field due to the two charges anywhere other than say the straight line joining the two charges, because electric field is a vector, so those two vectors have to be pointing in opposite directions for each other to cancel out. Here we are just talking about two numbers cancelling each other out. So yeah, if you have two oppositely charged things, and if there are points where KQ over R1 cancels K times 4Q over R2, and these charges have opposite signs, then those places will all have zero potential. Does that make sense? Any other place? Any other case where the potential will be zero? Is it possible that there is another point on this straight line here where the potential might be zero? Can there be any point here on this straight line? Or not? Yeah, there could be. How do I find that point? Let's say that, you know, I'm claiming that yes, there is a point here where the potential is zero due to both of these charges, and let's say that this is at a distance x2 away. You know, so this is another point, let's give it a name P2. So I claim that I can find another point where Vp2 is 0, and that means again I'm saying that V1 plus V2 is 0. For this point, how can I write V1? Let's say V1 is due to this charge plus Q. Can I write it as K times this Q plus Q divided by the distance x2, and that plus V2 will be K times minus 4Q. We are talking about scalars, so we need to put the signs in, there is no direction, divided by which distance? What is the distance of this point from minus 4Q? What is it? Yeah, it's 1 meter is this distance plus x2, right? Is everybody seeing this is 1 plus x2? And so this is the, so then you can see from here this should be equal to 0. If I take this to the other side of the equation, I get kq over x2 is equal to k times 4q divided by 1 plus x2. Is everybody appreciating why this is 1 plus x2? Because the distance of this charge minus 4q from this point is x2 plus 1 meter. We are not looking at any of these right now. We are just looking at some point over here. Okay, so let's divide both sides by kq. So what I get is 1 plus x2 is equal to 4 times x2. In other words, 1 is equal to 4x2 minus x2. That means 1 is equal to 3x2, right? And this means that x2 will be equal to 1/3 meter. So that means at a distance 1/3 meter away from this charge plus q, that means at a distance of 1 meter plus 1/3 meter away from minus 4q, the potential will be 0 due to both of the charges taken together. Does that make sense? Any questions, folks? All right, have a wonderful weekend. I'll see you guys next time.
Professor Singh is a lecturer in the physics department at the University of Pittsburgh. For more information about Professor Singh and her research, visit her website in the description below.